Welcome to G Fun Facts Online. Today, we're journeying into the immense darkness between galaxies, a void that holds the key to one of cosmology's greatest puzzles. We're going on a hunt for dark matter, the mysterious, invisible substance that astronomers believe makes up about 85% of all the matter in the universe. And our guide on this hunt is something unexpected, almost poetic. The faint, ghostly light of billions of stars that have been torn from their homes and lost in the cosmic wilderness. Let's start with the biggest structures in the known universe, galaxy clusters. Think of the grandest metropolis you can imagine, then scale that up to cosmic proportions. A single galaxy cluster can contain hundreds, sometimes even thousands of galaxies like our own Milky Way, all swirling in a colossal cosmic dance, bound together by an immense gravitational pull. But here's the mind-bending part. If you were to add up the mass of all the stars, all the gas, and all the dust that we can see in those thousands of galaxies, you'd only account for a tiny fraction of the cluster's total mass. The vast majority is completely invisible. This is dark matter, the unseen scaffolding that holds these galactic cities together. For decades, the central challenge has been, how do you map something you can't see? The answer, it turns out, was hiding in plain sight, or rather, in plain faintness. Astronomers are now using a diffuse ethereal glow called intracluster light, or ICL, to trace the contours of the invisible. So what exactly is this ghostly light? To understand it, you have to appreciate just how violent and chaotic a galaxy cluster is. It's a gravitational demolition derby that has been running for billions of years. Galaxies aren't static islands. They are constantly moving, interacting, and colliding. As a massive galaxy sweeps past a smaller one, its immense gravity acts like a cosmic tide, pulling and stripping away stars from the smaller galaxy's outer edges. Imagine a giant ocean liner passing a small fishing boat. The wake alone is enough to tear things loose. This process, known as tidal stripping, is one of the main ways intracluster light is created. Billions upon billions of these stars are cast out into the vast, empty space between galaxies. They become stellar orphans, no longer gravitationally bound to any single galaxy, but instead they begin to orbit the center of mass of the entire cluster. All of these individual, lost stars drifting through the intergalactic medium combine to create a soft, uniform haze. This light is almost impossibly faint, often 100 to 1,000 times dimmer than the darkest night sky we could ever experience on Earth. It's a true cosmic whisper. The idea of this light isn't new. It was first theorized back in 1951 by the brilliant and often outspoken astronomer Fritz Zwicky, the very same scientist who first found evidence for dark matter by noticing that galaxies in the Coma cluster were moving too fast to be held together by their visible mass alone. Zwicky predicted that this faint glow from stripped stars must exist, but it would take more than half a century for our telescope technology to become sensitive enough to actually see it and study it in detail. Tidal stripping isn't the only formation mechanism. Sometimes, entire small dwarf galaxies fall toward the center of a massive cluster and are completely shredded, spilling all of their stars into the intracluster space. In other cases, when two large galaxies merge in a spectacular collision, a process called violent relaxation occurs, which can also fling stars out of the newly formed system. A very small number of these stars might even be born directly from pockets of cooling gas in the intracluster medium itself. But the overwhelming majority are exiles, ripped from pre-existing galaxies. These stellar orphans aren't just a curiosity. They are forensic clues to the cluster's tumultuous past. When we study the properties of the light they emit, we find that the stars in the ICL are typically quite old and have low metallicity. In astronomy, metals refer to any element heavier than hydrogen and helium. So a low metallicity star is one that formed from a more primordial gas cloud, before generations of stars had a chance to fuse heavier elements and seed the galaxy with them. This tells us that the intracluster light is largely built up from the stripping of the outer fringes of large spiral galaxies, where older, metal-poor stars reside, and from the complete destruction of smaller, less evolved satellite galaxies. This process of building up the ICL has been happening over a long time, but it really picked up speed in the latter half of the universe's history. Most of it has accumulated since a redshift of about 1, which corresponds to the last 6 to 7 billion years of cosmic time. It's a sign that these massive clusters are still actively growing and assembling themselves today. Now we get to the heart of the matter. Why is this faint glow so profoundly important for understanding the universe? The true significance of intracluster light lies in its profound connection to dark matter. Think about it. Both the lost stars of the ICL and the invisible particles of dark matter are essentially free-floating within the cluster's gravitational field. They've both been liberated from the confines of individual galaxies. This means they are both subject to the exact same gravitational forces, and they both respond to the overall gravity of the entire cluster. As a result, the distribution of the intracluster light should exquisitely trace the distribution of the dark matter, where the cluster's gravity is strongest, which is precisely where the dark matter is densest. You should find a higher concentration of these lost stars. Therefore, the brighter the intracluster light, the denser the dark matter. It's like having a secret developer fluid that reveals an invisible photograph. By simply mapping this faint light, astronomers can create a direct visual proxy for the invisible dark matter scaffolding. This is a game changer. For decades, the gold standard for mapping dark matter has been gravitational lensing. This relies on Einstein's theory of general relativity, which says that massive objects warp the fabric of space-time. The immense mass of a galaxy cluster, mostly dark matter, creates such a strong warp that it bends and distorts the light from much more distant galaxies located behind it. By analyzing these distorted shapes, astronomers can calculate the total mass of the cluster and map its distribution. It's an incredibly powerful technique, but it's also laborious and complex. Another method involves observing the X-ray emissions from the incredibly hot gas that fills the space between galaxies. This gas, heated to millions of degrees, also traces the cluster's gravity. However, this gas can be affected by non-gravitational forces. For example, eruptions from supermassive black holes at the centers of galaxies can act like cosmic supervolcanoes, blasting energy out and pushing the gas around. This makes the gas a somewhat messy, less precise tracer of the underlying dark matter. Intracluster light offers a cleaner, more direct approach. Stars, like dark matter particles, respond almost exclusively to gravity. So by mapping the starlight, you get a much more faithful picture of the gravitational potential. And the evidence is stunning. The Hubble Space Telescope's Frontier Fields program, which took some of the deepest images of galaxy clusters ever, showed an excellent agreement between the maps of intracluster light and the dark matter maps created using gravitational lensing. The shapes, the contours, and the concentrations of both lined up with remarkable precision. But as with all cutting-edge science, there are complexities. The universe is rarely simple. Recent, incredibly sophisticated computer simulations suggest that the ICL might be what scientists call a biased tracer. This means that while it follows the general shape of the dark matter halo, it might not be a perfect one-to-one representation. These simulations indicate that the stars making up the ICL might have slightly different orbits and energies than the dark matter particles. They might be on paths that take them closer to the cluster's center, making the ICL slightly more centrally concentrated than the dark matter it traces. Understanding these subtle biases is the next step for scientists, allowing them to refine the ICL method into an even more precise cosmological probe. And we can't forget the immense technical challenge of even seeing this light. The Dark Energy Camera, or DE-CAM, mounted on the Victor M. Blanco 4-meter telescope in Chile, has been a hero in this field. In one landmark observation, astronomers used DE-CAM to stare at a galaxy cluster named Abell 3667 for a staggering 28 hours of total exposure time. The result was a breathtaking image that revealed a glowing bridge of stars connecting the cores of two smaller galaxy clusters in the process of merging. It was a snapshot of the ICL being actively formed, a visual confirmation of the violent processes at play. The James Webb Space Telescope has now opened an entirely new window. Its unparalleled sensitivity, especially in infrared light, is perfectly suited for detecting the faint glow of these old, cool stars. In early observations of the cluster SMACS J0723, JWST was able to trace the intracluster light out to a distance of over 1.3 million light-years from the cluster's core, revealing the rich and complex history of its formation in stunning detail. And the future for studying this faint light is, ironically, incredibly bright. The next great leap forward will come from the Vera C. Rubin Observatory. Its primary mission, the Legacy Survey of Space and Time, will be revolutionary. For 10 years, Rubin will image the entire southern sky every few nights with its enormous 3.2 gigapixel camera, creating the deepest and widest movie of the universe ever made. For ICL researchers, this is a treasure trove. They will be able to stack images, digitally combining hundreds or thousands of pictures of the same patch of sky to create ultra-deep exposures. This will reveal the intracluster light around countless galaxy clusters with unparalleled clarity. We won't just have a few case studies. We'll have a cosmic census of ICL, allowing us to see how it varies with a cluster's mass, age, and merger history. This will provide an invaluable resource for creating the most extensive and detailed map of the universe's dark matter structure ever conceived. So by tuning into the whispers of these billions of lost stars, we are piecing together the epic, violent history of how the largest structures in the universe are built. And in doing so, we are literally illuminating the invisible. The ghostly glow from stars that no longer have a galactic home has become our beacon, guiding us through the dark to reveal the fundamental scaffolding that underpins our entire cosmos. They weren't truly lost after all. They were just waiting to show us the way. Thank you for listening to G Fun Facts Online.